We're going to do a lesson on polynomial functions and their graphs. Now, a polynomial, you know, poly means many, nomial means number or term, but we're going to define polynomial as the sum of monomials. Now, polynomials are made up of coefficients and variables. The variable that we're using today is x, and I'm going to represent my first coefficient as a sub n, and we're going to represent our first variable as x to the n power. We don't know how many terms we're going to have, so we just represent our largest exponent with an n. Then, as we go down, we just subtract from the n. And these don't represent any particular numbers. This is a general standard form for a polynomial. Okay? And then we're going to put some dots. As you know, that means we keep going with following the same pattern until we come to the end of our polynomial function. And we would have a times x. Now the n there is understood to be 1. And then our very last term is a constant, a sub 0. And what you see here is that we're reducing our variable, or the exponent for the variable, by 1 every time until you get down here with our understood 1. Okay? And then down when we get to the end, we have a 0 exponent, which is just 1. Now let's identify the different parts of our polynomial. First of all, our leading coefficient. The coefficient is the number in front of the variable. Leading coefficient is a sub n. And the degree, how big is our polynomial, is going to be n. That's the largest exponent that we have present. Now for this to be a polynomial function, our exponents must be whole numbers. And that means no negatives, no fractions for exponents. And at the very end, our constant term is going to be that little number all by itself with no variable. Now standard form simply means that it's written in descending exponent order. So you start with the biggest exponent and go down. So we're going to work with these examples and this information. So what we're going to do is identify whether this function is a polynomial function. And so what I'm looking for is the exponents. Now, are the exponents whole numbers? Yes, they are. I don't see any negatives, and I don't see any fractions for exponents. And so the answer for this one is yes. This is a polynomial function. And it's also asking what the degree is. Now the degree is the largest exponent. And the degree here in our largest exponent is that 3 right there. And the question's also asking what is the leading coefficient. And I'm going to abbreviate. Okay, well, the leading coefficient is found the same place the degree was, and that is where the largest exponent is, and the coefficient here is 1. Okay, moving on to example 2. We're going to ask the same questions. So I'm looking at my exponents. I have a 4 here, I have a negative 2 here, This one's 0. And that one's 4. The only one that doesn't meet the criteria is this one. I have a negative. A negative 2 is not a whole number, it's an integer. And so this is not a polynomial function. However, it does have a degree because it does have a largest exponent, and the degree is 4. And the leading coefficient here is deceptive because I have two terms with a power of 4. So I'm going to actually combine these two like terms, which gives me a leading coefficient of -2. Now, polynomial functions have certain characteristics that can be found on the end of the graphs, thus the term and behavior of polynomial functions. And the behavior of the function is determined a lot of times, or every time, by the degree of the function. You see right here, degree of the function, and the sign of the leading coefficient. Now, all the polynomials are going to have the same basic shape if they have certain characteristics. So I'm going to draw for you a polynomial function that has an odd degree. Now that means its largest exponent is going to be an odd number. And so what I'm going to draw for you is one that has an odd. Now these are very general equations. This is an example of a polynomial function that has its highest exponent being odd, which means it's 3 or 5 or 7, and as long as it's an odd number. This one also happens to have a leading coefficient that is positive. So the very first coefficient is going to be positive. So let's look at the behavior on the end of this. Let's look down here. Down here, as we're going further and further left, look at what's happening to our y value, or f of x, is going down. And that means that it is approaching, that's what that arrow means, -infinity. But also look at the x right here. It's also getting further and further negative. And so that means on this end, as f of x is approaching -infinity, x is also approaching -infinity. Now let's look at this other end. As we're going up and up and up, my y is getting more positive, and so is my x. And so that means that as f of x approaches positive infinity, my x also is. And this is a pattern that you can find with any odd degreed polynomial with a first positive exponent. Now let's compare it over here. I'm going to put another odd polynomial, but we're going to change the sign of our leading coefficient to negative. And I'm going to zoom in a little bit. So I want another odd one. And this time I want a negative leading coefficient. Give myself some more space here. Well, what you may remember from when we were graphing other shapes, absolute values, parabolas, that if the leading coefficient changed sign, the graph would flip over. And so that's what happens here. So this one does this. I'll put the arrows on the end to show they keep on going. And so let's see what happens to the behavior of the ends. So down here on this end, this keeps going up. It means my y is getting larger, so I'm approaching positive infinity, but I'm on the left end of this graph, so my x is approaching negative infinity. Okay, let's look on the other end. My y is going further down, okay, but my x is becoming more positive. So, negative infinity, positive infinity. So what I want you to look at for these odd graphs, for these odd degree graphs, is that the y's are going in opposite direction. So if your y values on the ends are going opposite, you have an odd graph. So let's look at even graphs. And these are general shapes for all even graphs. And I've already given you a hint. I want an even degree here. And I'm going to start with a positive leading coefficient. Now, a good example of an even degree are the parabolas that we had been graphing, like this, because these are squares. But I want to give you an even more general graph to use. And we're going to do one that looks like this, kind of like a W. It may have more curves or fewer curves, but it has the same characteristics. If you notice, the ends, the y values, are going the same direction. That is a characteristic of an even degree polynomial. So f of x on the negative end is going up. It's also going up on the positive end. And my stylus is not cooperating. There we go. Now, something else you may have noticed is down here, the x is always going to be negative. Over here, the x is always going to be positive. Okay, so just like the odd polynomials, if we change the leading coefficient sign from positive to negative, all we're going to do is flip it over. So let's come and look at the other graph right here. So our degree here is even, 2, 4, 6, 8, 1,000. And here my leading coefficient is going to be negative. And we've already established down here this x is going to be negative infinity. This x is going to be positive infinity. And the general shape for a negative, it's going to be kind of a M-like. And what you're going to notice is this time down on the left end, going down to negative infinity. And so is this one. So let's try using this information and see if we can make some decisions about some graphs. Okay, so we're going to take what we just learned about end behaviors of graphs and make some decisions about these polynomials I'm about to give you. Now, it's a good idea to make a sketch. So I have a negative and it's an even, and what I learned from my graph is that it's going to be kind of shaped like that. Okay, so let's see what happens here. So as x approaches negative infinity, that's this end, my y value is also approaching negative infinity. And since it's even, that means the y value is going to be the same on the other end. So even, equal. Okay, so let's look over here. Now this isn't odd, and it's positive. And so this shape of this graph is going to be kind of like that. So what I care about is what's happening on the ends. Okay, down here where x is negative infinity is going down. So my y is also approaching negative infinity. And odd is opposite, so that means on the other end my y is going the opposite direction. Okay, moving on, we're going to look at combining polynomials. We're adding these. This is just a matter of collecting like terms. So I have an x cubed here, x cubed here. We're just going to add those. So negative x cubed. I have an x squared here and an x squared here. We're adding them. So plus 2x squared. 3x here. Negative 4x here. Again, we're adding them. And then the very last one are my constants. Okay. Now this one, example 2, you need to be careful because you are subtracting, which means that negative needs to be distributed everywhere. So here's our cubes right here. And you get a negative 7x cubed. Here's our squares. Positive 2x squared. Here's my x's. Positive 2x. And last, my constants, which is negative 15. Now if we're multiplying, you could multiply this out, make a big line of terms, and then collect your like terms. But I like to do my multiplication vertically. And let me show you what I mean by that. What I like to do is I'm going to take my first term here and I'm going to distribute it through that parentheses. And that gives me 6x squared, no, 6x cubed plus 9x squared. Okay, I'm done with the 3x squared, so I'm going to come over here to 3x. I'm going to distribute that through the parentheses. So 3x times 2x gives me 6x squared. So I want to line the 6x squared up underneath the 9x squared. And then I'll distribute again and get a 9x. And last, I'm going to take this 5 and distribute it through, and I'm going to go ahead and line them up as I do my multiplication, my like terms. Then I just add straight down. And what that gives me is 6x cubed plus 15x squared plus 19x plus 15. All like terms are collected, and I have my answer. So I'm going to stop the video, you try example 4, and then I will come back to you with the answer. Alright, here's the last example. And I hope you got that answer. The last thing that we're going to do is I'm going to give you some rules for special products, and I do have a bit of a typo on this one. This is supposed to be, mark that out, that's supposed to be a minus. That's our friend, the difference of squares. So some special products, if you see this pattern, you'll have a squared minus b squared. Now these two are perfect square trinomials. They fit this pattern. If you're adding, you add. If you're subtracting, you're going to subtract the middle term. And this is all just the result of foiling. It just shortens it a little bit. Now, I have perfect cube trinomials, and they fit this pattern. A cubed plus 3 a squared b plus 3a b squared plus b cubed. That's the result of foiling that and then multiplying again. And then the very last one. It's exactly the same except every other sign is changed. Just like that. So try multiplying it out, see if it works for you. And that's the end of this lesson.